Yeah, sure. Yeah. What is time now? 10:30. Okay. So 11:15 we are going to take another break for 20 minutes. Okay. So we are going to start our second topic today. Second topic on biological waste treatment processes, number 1, and under number 1 we are going to cover composting. Okay. So we already learned that actually composting, it's an aerobic bioprocess where microbes, okay, and some other large organisms actually can degrade or transform the organic content in your solid organic waste like food waste, yard waste, and convert them into a soil like material called compost. Okay. And biodegradable material, so not necessarily just microorganisms, okay, you can utilize for composting. Sometimes some vermicomposting, there is something called vermicomposting. So even larger organisms like earthworms can also be used for composting process. And as you can see here from this picture, here is organic waste, and after conversion to compost, it's like more like soil type material, and it's very rich in nutrient. Okay, so it can serve as a slow release fertilizer. Okay, slow release fertilizer, and it can actually also reduce the use of your chemical fertilizer, right? And another benefit of using compost is the water holding capacity of compost is very high. So that means if you use compost for your agriculture, you are going to need less watering. Okay, so it can also save your cost for irrigation. So the fundamental of composting, so it mostly done by microorganisms, but other organisms can be used, as I mentioned. And carbon like material is actually converted to carbon dioxide, water, humic and product, which is a kind of a compost. Okay, and the process also actually produce heat. Okay, so that means like aerobic activated sludge process, composting process, we also need to provide air in the process, because those microbes, they need oxygen as electron acceptor. Okay, you remember that, that's good. Okay, so yeah, so we need actually oxygen in the process, and the process is going to produce carbon dioxide, water, and release heat, but at the same time some odorous compound can also be generated like ammonia, sulfide. And for like any biological process, okay, there are some optimum range of operating or environmental parameters for composting, and one critical factor in composting is carbon to nitrogen ratio in the feedstock. Okay, so optimum carbon to nitrogen ratio for composting process is 30:1. Okay, but well, if it's 25:1 or 35:1, still it's okay. But if you are actually using, if your primary feedstock is, let's say, 10:1, then it's not a like good idea to use that item as a sole feedstock for your composting process. So to carbon to nitrogen ratio, it's a big factor in composting or any biological process. Okay, because microbes, they produce carbon more quickly, right? Even if you remember, like we are writing a chemical formula C5H7O2N, right? They need more carbon and less amount of nitrogen. Composting process, you also need to make sure that you have enough moisture, okay, because microbes, they also need water in the process. So 50 to 60% moisture content you have to maintain. Oxygen content 10 to 15%, okay, because you need oxygen as electron acceptor there. pH, like they are mostly bacteria, okay, so 6 to 8 neutral pH. And particle size, it's very important. You have to make sure that particle size is between 0.5 to 2 inch, okay. And sometimes it's kind of problematic because solid waste is kind of very heterogeneous, right? So you can have a wide range of different sizes, particle sizes, but sometimes pre-processing may be required. Okay, but for composting, pre-processing of feedstock is not a common practice. But if you have large particle size, that means your composting time gonna be more. Okay, you have to actually keep them for longer time to composting process to be completed. And steps involved in composting are actually inspecting the feedstock. So first of all, if you receive a feedstock for your composting, first you have to inspect the feedstock and you have to actually remove any undesired items. So let's say if you have any plastic bag, some broken glass or any sharp material, okay, you have to actually remove them, you have to take them out, otherwise they are going to be in your final product and the quality of compost not going to be good, right? And even sharp material, if it's there, it's also not for safe. Okay, and then after inspection and removing undesired items, you have to actually prepare the feedstock. So what is preparation? We just mentioned that carbon to nitrogen ratio has to be like within some optimum range, like 30:1, right? So now let's say your facility received a feedstock, but carbon to nitrogen ratio is not within a proper range, then you have to actually find another complementary feedstock that you can mix together, okay, and reach some optimum carbon to nitrogen ratio. Okay, and then after your feedstock is ready, you can start your main process, which is called active composting and curing. Okay, that's kind of like the longest part or the key part of your composting, and there are 3 different phases in composting. Okay, so first is, it's more like, you know, we talked about microbial growth curve yesterday, right? So composting, it's also a batch process. Okay, so you have almost the same thing, lag phase and exponential phase, stationary phase, and you know the decay phase in composting we call it curing phase. Okay, so lag phase, active phase, and curing phase, and then finally after composting process is done, typically they are sell it to the market. You have to actually final compost after processing is done, you have to screen them, okay, before you actually kind of bag and sell it to the market. So inspection of feedstock include removing of unacceptable or non-compostable item that can actually impact the finished quality of the finished compost product quality. Okay, and inspection and preparation may include different steps. So one thing I mentioned, like you know, mixing different types of feedstock to achieve some desired carbon to nitrogen ratio. Another thing could be particle size. Okay, so particle size, if it's too large, then that means your composting process is going to be very long, and you don't want that, especially when you are limited by footprint, right? In that case, maybe you may go with some pre-treatment process to actually kind of maybe grinding to reduce the particle size, because microbes like they cannot actually break down large particle, right? So you need sometimes need some sort of pre-treatment. Okay, and so carbon to nitrogen ratio, it's an indicator of relative amount of nutrients and carbon. Okay, so low carbon to nitrogen ratio means high nitrogen content, and high carbon to nitrogen ratio means higher proportion of carbon, and both are actually not good. We know that actually, like microbes, they have more they kind of more quickly or faster metabolism for carbon. Okay, but still you need nitrogen as a nutrient source. Okay, and so that means to make sure that we can achieve a desired carbon to nitrogen ratio, and as I was mentioning, we don't need exactly 30:1. If it's 25:1, 35:1, it's still fine, within some good range. So this is kind of like, step by step. First we need to identify the primary feedstock for our composting, and then we have to know the desired properties. Okay, so we have to characterize if carbon to nitrogen ratio not within a range. We have to identify a secondary feedstock, we have to blend them. Okay, but we have to know, okay, how much of the primary feedstock is mixed with how much of our secondary feedstock, right? So we need to know that. So first of all, we have to characterize carbon to nitrogen ratio for our primary feedstock. We have to characterize carbon to nitrogen ratio for our secondary feedstock. Okay. So we need to know how to calculate proper mixing ratio. So let's see an example. Okay, how we can do that. So, but before that, a typical carbon to nitrogen ratio in different types of organic waste that is actually generated from our household. Food waste 15:1, okay. Green grass 10:1, leaves 55:1, wood chips 200:1, newsprint 400:1, cardboard almost 600:1, right? None of them are actually 30:1. So that means if you use a single feedstock, it's not going to work. Sometimes actually compost, we can do it actually in our backyard, right? So I'm not sure. Someone you do composting at home? Huh? Okay. So I also actually do composting. I used to do composting, okay, during summer. But typically what happened, like, you know, mainly for vegetable scraps, okay. So we kind of put it in some bucket, okay, with some inoculum, and then leave it. Typically if I do it this year, I use it in the following year, okay, because it takes really long time, because I don't actually maintain any carbon to nitrogen ratio or anything, right? So it's kind of like, you know, more natural composting. So that's why it takes almost a year to get the compost. But think about facility, they cannot keep your garbage for a year, right? The composting process to be done. So if you do in centralized facility, you have to make sure that everything within optimum range, you can finish the process within few weeks and you can move on with the next batch, right? So this is a simple equation that we can actually use to calculate how much of primary feedstock to be mixed with how much of secondary feedstock, okay, to actually achieve some sort of target carbon to nitrogen ratio, okay. So you can see here dry weight of carbon in feedstock 1. So number 1 is my primary feedstock, and dry weight of carbon in feedstock 2 is my carbon in my secondary feedstock, okay. And you can see here in this equation, so dry weight of, we need dry weight of carbon and dry weight of nitrogen for both. And why dry weight? Okay, because we have to consider dry weight because our organic waste contain a significant amount of moisture, right? So that's why we consider dry weight. And here in this equation, S is the mixing ratio. So the amount of feedstock needed per kilogram of primary feedstock, okay. So that's the equation. So let's see an example. Blending of waste to achieve an optimum carbon to nitrogen ratio. So for a composting process, solid waste A with a carbon to nitrogen ratio of 40 is to be blended with solid waste B, and for solid waste B carbon to nitrogen ratio is 5, okay. So we have primary feedstock which is carbon to nitrogen ratio 40, we have secondary feedstock very low carbon to nitrogen ratio 5. So now my equation is, and moisture content for A is 40%, moisture content for B is 60%, and nitrogen content is 0.2%, and nitrogen content for B is 1%. So I want to know if with 1 kilogram of A, okay, how much of B should be mixed, okay, to achieve carbon to nitrogen ratio of 25, okay. So we are going to go back. So we can start with a basis of 1 kilogram, okay. We can consider, okay, I have 1 kilogram of waste, okay. So and I know that there is moisture there. So if I have 1 kilogram of waste, if there is 40% moisture in there, that means dry weight gonna be 60%. So if I have 1 kilogram of waste, 600 kilogram gonna be the dry weight, right? And out of the dry weight, I have 0.6, yeah, 0.2%. So 0.2% means 0.002, 0.2 divided by 100. So I have, out of that 0.6 kilogram, I have 0.0012 kilogram of nitrogen.
It should be 0.02, right?
it was 0.2.
Yeah, it's okay.
Yeah. So now I know carbon to nitrogen ratio is 40, right? So if I 40 multiply by the amount of nitrogen, I can get the amount of carbon that I have, right? So for the second feedstock, we can do the same thing. For B, we know that moisture content is 60%. That means dry weight gonna be out of 1 kilogram, 400 gram gonna be the dry weight for B. And nitrogen content was about, I think, 1%. Okay, so that means multiply by 0.01, so 0.004 kilogram. Okay, and then carbon to nitrogen ratio is 5. So now I have both, like in 1 kilogram, how much carbon and how much nitrogen we have in both, feedstock, we have the number. Okay, so now I am ready to use my equation. So I can actually plug those numbers there. So S is 0.2. So that means with 1 kilogram of feedstock A, I have to add 0.2 kilogram of feedstock B, and that gonna give me carbon to nitrogen ratio of 25. Okay, so that simple calculation actually can help you to estimate, okay, how actually we can actually mix different types of feedstock and make it ready for composting. And not necessarily just for composting. This concept can be used for other biological process like anaerobic digestion process, because carbon to nitrogen ratio is something important for any biological process. So you can actually use this same approach like for even for anaerobic digestion process. Okay, so that's why we covered this topic now in this composting chapter. So we are not going to talk about this again in anaerobic digestion, but you may need even for anaerobic digestion process, optimum carbon to nitrogen ratio is almost the same, 30:1. Okay, because they are heterotrophic biomass in both process.
What is the significance of S?
Huh?
How the S is defined?
Sorry?
How is the value of S is defined?
So 0.2 kilogram. So we have to, if I have 1 kilogram of feedstock A, okay, so before composting process, to reach carbon to nitrogen ratio of 25, I have to add 0.2 kilogram. So that means your total gonna be 1.2, right? And 1.2, you are gonna have carbon to nitrogen ratio of 25. Make sense? Okay. Okay. So another part of preparation could be adding bulking agent. So what is bulking agent? Sometimes, so composting process need oxygen. Okay, and it's not like wastewater treatment plant that you are 24/7 you are actually supplying air in the process, right? So composting process typically we don't provide active air circulation. Sometimes what we do, we mix the feedstock, okay, and then we leave it for like a week, and then after a week we come back, we kind of turn them, okay. So it's not active like 24/7 aeration. So that's why, but sometimes like feedstock may be very compact and they are not going to be enough diffusion of air in the compost pile, right? So that's why some facilities they add some material called bulking agent. Okay, bulking agent can be straw or wood chips. Okay, so when you mix wood chips and straw with your feedstock, okay, they are typically not easily biodegradable, right? So wood chips is not going to be easily biodegradable. Like if you compare with food waste and wood chips, food waste is going to be degraded, but wood chips it needs really long time to degrade, right? So but when you add both kind of material, you can have like more pores, and actually air can easily diffuse in the compost pile. So that's why those materials are actually added as bulking agent. And bulking agent they have little to no decomposition, okay, and after the composting process is done, okay, you can simply screen them, okay, and reuse those bulking agent again for your next batch of composting. So that's how it looks like composting, and it can be reused after screening of final step. So now after you prepare your feedstock, you start the process, and then first step gonna be lag phase. Okay, first step gonna be lag phase, and lag phase is period of adaptation of microbes, as we learned in yesterday in microbial growth curve. So microbes, they need some time to adapt with the feedstock first, okay, and then they are going to actually start to break down the organics slowly, okay, and microbes, they are going to start to grow, okay, because microbes, why they degrade, we know that actually they want to grow. It's a part of their growth process. So they are going to actually start utilizing different types of organic sugar, starch, cellulose, amino acid that is actually present in your feedstock, and they are going to start to grow. And so that means microbial activity going to increase, and at that time what you are going to see, if you remember one of the previous slide, so the process also generate heat. So you are going to see in the compost pile, temperature going to start to increase, okay. So one of the important monitoring parameter in composting process is temperature. So temperature is an indication that actually your composting process is running properly or not. So when you are going to see your temperature started to increase, that means the process started, your lag phase is ending and it's kind of reaching active phase. So active phase, you are going to see exponential increase in microbial activity, which going to be,
Is it log phase?
huh?
Is it log phase?
It's kind of log phase, but they call it active phase. Yeah. So it's like, you know, log and stationary, I would say. So log and stationary combined together, and we call it active phase. Different book, different, but again it's exponential or log phase plus stationary phase. So it's indicated by a increase in temperature, okay. So that temperature increase gonna continue until microbes, they have enough food, okay, they have enough food. So when you are gonna see temperature started to decrease, that means your curing phase started and your active phase kind of ended. So temperature is a monitoring parameter. But what if you see temperature starting and suddenly next day, instead of like, you know, gradually decrease in temperature, it's kind of sharply, maybe from 60 degrees Celsius, next day if you see 25 degrees Celsius, then there is something wrong, okay. There might be some sort of inhibition, okay, or maybe microbes, they don't have enough oxygen, so they kind of, you know, they are completely got inhibited. So there could be some sort of malfunction. So that's why temperature is in centralized facility. Maybe when you do it at home, you don't actually monitor temperature, but when you do it in the facility, you have to make sure that you monitor the temperature, because that's kind of like give you an idea what's going on in the process. So but at the same time, you have to make sure that temperature should not go above 70. If it goes above 70, then it's a problem. You are going to actually kill all the microorganism, right? It's mostly like you are sanitizing. So but again, a sudden drop in temperature during active phase is an indication that some sort of actually malfunction happened, okay, and you have to take immediate action, okay. One thing, you can go and check pH. If pH is acidic, okay, then that could be a problem. If you don't have enough oxygen in there, that could be another problem, okay. And the final step is curing phase. So curing phase means microbes, they do not have enough of organics, so they are kind of you know, their activity is declining over time. So you are going to see gradually temperature going to start to decrease, and curing phase can be you know, like it depends on the what kind of feedstock that you are dealing with. Curing phase, for some feedstock it can be very short, for some feedstock it could be very long, okay. And it depends on feedstock, it depends on what kind of process you are using, okay. Maybe you know, if kind of like, you know, mix the feedstock in more regular basis, the process is going to be faster, right. So this is a typical temperature profile in compost pile, okay. So typical temperature profile, you can see in the decomposition. So decomposition is basically lag and active phase. Okay, you are gonna see temperature starting from ambient temperature, it's kind of increase and go close to 60, and then it slowly started to decrease. So this part we call it maturation or curing, and this part we call decomposition, or different book they use different term, but decomposition is lag plus active phase, and maturation is basically curing phase. So when you do it in industrial scale, there are different options that you can use. Okay, there are different strategies that you can use. So and most of the centralized facility, they have 3 types of system that can use. So one is called aerobic static pile. Okay, so this is one process that you can use. Another process is windrow composting. So basically you have if you can do it outside, and you can actually pile the composting material in different windrows, okay, and leave it for some time. Some facility also use vessel type or bioreactor type composting process. And why is that? Because when you do it in vessel, it's easy to actually control some of the parameter, okay, and control and monitor some of the parameter is much easier when you do it in aerobic static pile or windrow composting. But again, the selection of the process depends on how much money you have, right? Everything, end of the day, it's about how much capital investment you need, okay, and land availability. So typically windrow composting, you need much more larger space, but if you go with vessel type, okay, you can build a vessel like a silo type, okay, so that means you need a small footprint, okay. So it depends on many other factor, but obviously windrow composting is the easy one, easy to actually control. When you go with vessel type, you need much more skilled people to operate this kind of facility. So windrow composting is the simple process, okay. So you basically compost, you can do the compost by piling solid waste into a long semicircle shaped piles. You can see here in this figure, okay. So you can have multiple those semicircle shaped piles where you can actually stack your waste, okay, and you don't have any active aeration, but maybe every weekly or every couple of weeks you have to come back and turn them, okay. So then you have enough oxygen in the compost pile. And piles are usually actually they aerated either manual or mechanical equipment, okay. In this kind of, if there is large facility, maybe you cannot do it mechanical, you need some you cannot do it manually, you might need some mechanical equipment to do that. And that's why you can see with between 2 piles you have some space, right. So if you have any mechanical equipment, you need some space to actually move them, right. So that's why you see there are some space between each windrows.
This is basically like people do in rice mill with rice.
Yeah.
Same technique.
Yeah. And this method can handle large quantities of diverse types of organic waste. But one of the major challenges, weather condition. Okay, if you have heavy rain, then everything gonna be washed away, right? So that's a problem. Cheap thing always come with lot of challenges, right? So it's kind of, you have to accept that. Another process is almost same, but instead of passive aeration or intermittent aeration, you can actually have a network of pipe, and then you actually kind of pile your waste or compost material on the over that network of pipe, okay, and whenever needed you can run the pump, okay, or blower, and you can actually provide air in the process, okay. So that's kind of easier, you don't need to move any equipment around. And aerobics, vessel type of or bioreactor type composting process, okay, that is mostly used in some developed countries, okay. For example, in Canada we have 6 months winter, right. So that means actually we cannot do it outside most of the time. So, but even in winter, we cannot stop eating during winter, right? So, we have food waste generated throughout the year. So, what we would do? So, that is why sometimes actually some facilities they used vessel type or bioreactor type of composter. Okay. And actually, like previously we used to have a composting facility that could actually process 80,000 tons of solid waste every year, which was actually in our city, that was one of the largest in North America composting facility. But that facility was closed, and then now actually municipality is moving more towards anaerobic digestion process. Yeah, but still we do composting in summer months. They are actually done in outside, but other city. So there are two big cities in our province, Edmonton and Calgary. But Calgary right now they use this kind of process. So this method can also process actually large amount of waste, okay, because you can have like silo type. You have like you can have some bioreactor with like tall bioreactor, like silo type design. So instead of like you can actually build them, or you can actually treat more waste, okay, with small footprint. And this kind of bioreactor type organic waste, bioreactor type system can handle any kind of waste. And why? Like you can use meat, animal manure, biosolid, food scraps. Sometimes when you do it outside, if you have, let's say, meat product or manure, they create odor. Okay, and if those facilities are near residential areas, people gonna complain. Okay. So that's actually major problem, because sometimes like typically in Canada, most of the waste management facility, they are typically far from residential areas. Okay, otherwise people gonna come and complain about odor. So odor is a major problem, but if you have bioreactor type, you can easily actually control the odor problem. So the process actually comes with this kind of process comes with lot of control system and lot of sensors, okay, but at the same time it's gonna be more expensive, as you can expect. Okay.
So is it feasible for hilly area, mountain?
Well, it depends, like you can actually do it anywhere. You can build like there are drum, silo type, or concrete line trench. Okay, so you can build it anywhere. It doesn't matter. Like in hilly areas, you can build houses, right? So why you cannot build some facility like this?
Temperature doesn't have any effect.
Sorry.
Temperature, if it is beyond 0 degree minus.
Oh, at winter it might be problematic. Yes. In that case, you have to possibly like supply hot air in the process. Yeah, so that's why actually in our in Edmonton, the anaerobic digestion facility, it was actually large steel structure building. So they actually have everything inside the building, and building during winter months it's heated. So they used to maintain 37 degrees Celsius inside the building always. And air was always recirculated. There was a biofilter outside, so any air, okay, was continuously 24/7. It was recirculated between biofilter. So exhaust air was going to the biofilter, treated, and then you kind of bring it back. So yeah, like temperature could be a problem.
What is the maximum amount of volume it can have?
It depends. I think different design comes with different capacity. Okay.
How about the seeding? Is there any inoculation type?
Inoculation, yes, yes. You have to actually, yeah, mixed. Yeah, you have to add some. Maybe you have to actually collect some inoculum from your first batch, like obviously before curing. Okay. And then use that as an inoculum for the second batch. So we have three options. We have windrow, we have aerobic static pile, we have reactor in vessel. And if we go from windrow to reactor vessel, the cost, operating skill, and process and emission control you have to invest more. So that process is going to be more expensive. But windrow, we need more space, but it's a cheaper option. So if you have open space, okay, and if weather is good, then possibly windrow composting is the most cheapest option that you can select, and it's most cost effective and most widely used process. And typically those for windrow composting, okay, they are actually organic material. They are kind of they are formed into long piles, okay, and they are typically semicircle shape, okay. They are in semicircle shape, may not be perfect semicircle, but for our engineering calculation we consider it's perfect semicircle, right? I cannot go and measure whether it's perfect or not, right? So for engineering calculation we consider it's perfect semicircle. So, and windrows are typically 1.5 to 3.5 meter high, okay, so you cannot go beyond that, and typically 3 to 6 meter wide, okay, and between two windrows you have to keep some space, 1 to 5 meter, to make sure that you can move your mechanical equipment for aeration, okay. So let's see an example. Calculate the total area and number of semicircle windrows required for composting, okay. Our total volume of waste to be composted is 50 meter cube per day. So let's say the facility is receiving 50 meter cube per day, and the composting time total time gonna be close to 100 days, right? So for 100 days, whatever the waste is collected, we collect them in batch, and we actually gonna run some composting process in batch. And now we consider the length of the windrow is 25 meter, okay, and space around the perimeter. So this is something like, let me draw it on the board. So you have multiple windrows. So you have to keep some gap with two windrows, and you also need to keep some gap here on each side. This is called space around the perimeter. Okay, so we are saying that the length of the windrow is 25 meter. So this is 25 meter. And space around the perimeter is 3 meter. Okay, so we are saying here it's 3 meter, here it's 3 meter, here it's 3 meter, okay, 3 meter. And distance between two windrow is 4 meter. So between two windrows we have to keep 4 meter. So I want to estimate, okay, what is the total area that I need if I decide to go with windrow composting, okay, and how many semicircle windrows we can have, okay. And windows we can go up to 8 meter diameter, okay. So now every day we are generating 30 meter cube of waste, okay. So in 100 days we are going to have 5,000 meter cube. So now surface area of the windrow, so they are semicircle, and for circle it's pi r square, right. So semicircle pi r square divided by 2. So you have 25.13 meter square surface area. Now we know the length, which is 25 meter. So if I area multiply by 25 meter, I can get what would be the volume of each windrow, okay. So what is the total amount of waste or volume of waste we can have in each windrow, right. So 25.13 multiplied by 25. So each windrow we can have about 628 meter cube of waste, okay. So now my total waste is 5,000. So if I divide 5,000 by 628, we need about 7.96 windrows, but I cannot, we are not scientists, we are like in engineering we kind of like to round numbers. So instead of 7.96 I will consider, okay, we are going to have 8 different windrows. Okay, so we are going to have 1, 2, 3, 4, 5, 6, 7, 8 windrows, and each side we have to keep space around the perimeter 3 meter. We have distance between each windrow 4 meter, and length is 25 meter, right? So now I can easily calculate the length. What would be the length? So space around the, so 25 meter, and on both sides 3 meter, 3 meter. So I have 25 plus 2 multiplied by 3, right? So 31 meter, my length gonna be 31 meter. But now what is the width? So width gonna be, you have diameter 8 and you have 8 windrows, right? So 8 multiplied by 8, 64. So 8 multiplied by 8, 64. We have gap between two windrows 4, and I have 8 windrows, so that means we have 7 gaps, right? So 7 multiplied by 4, okay, 7 multiplied by 4. Now on both sides I have 3 meter and 3 meter, okay. So 3 plus 3, so or 3 multiplied by 2 is 6. So 64, 28. Can I have 5 more minutes? Yes. Okay, so I have just one more example and then we'll take a break. Okay. So we have on both sides, so width gonna be 98 meters. So if I multiply 98 by 31, so this is gonna be my area. I'm gonna need about 3000 square meter of footprint if I want actually like go with windrow composting. So another example, after this example we can go for tea break. Okay. So calculate the number of semicircle windrows and distance between two windrows required for composting. So here the diameter of the window is 3 meter. So height gonna be, because we consider it as perfect semicircle, 1.5 meter, and length is 15 meter. We want to know how many windrows we need and what should be the distance between two windrows if we have some limited space like 1245 meter square. Okay, and every day 14.6 meter cube waste is generated, and we assume that our composting process gonna take 50 days. So each batch gonna run for 50 days, and space around the perimeter is 2 meter, like previous example is it was 3 meter. So now let's see. So first we have to estimate what is the total volume of OS that we are going to be dealing with. So 50 days multiplied by 14.6, so 730 meter cube. Now I can calculate the area of semicircle, which is pi r square by 2, so which is 3.53, and we know the length, which is 15 meter, and 15 meter here you can see. So volume of each window gonna be about 53 meters cube, and our total volume of waste is 730 meter cube. So we need about 13.78, or I can round that round up, I can make it 14. Okay, so we are gonna need 14 windows. So now here we don't know, we want to estimate what should be the distance between two windows, right? So like previous example we knew what is the distance between two windows, but here we don't know. So first we can actually calculate length. So length gonna be 15 meter plus on both sides you have 2 meter and 2 meter, right? So 15 plus 4, 19 meter is my length. But width I have 14, right? 14 windows. So 14 multiplied by 3, okay? 14 multiplied by 3, and distance between two windows I don't know, but I know I have 14 windows, right? That means I'm gonna have 13 gaps. Okay, I can consider, okay, you know what, the length gonna be x. Okay, so 13x, okay, and space around the perimeter on both sides going to be 2 meter and 2 meter. So 4, so 46 plus 13x. So we know the length, and for width we have this, okay, but we know the total area. So 46 plus 13x multiplied by 19, and my total area is 1245 meter square. This is my total area available. So I can easily solve this, and x is 1.5. So that means with this limited space I can only keep 1.5 meter of distance. Okay. Yeah. So here we are finishing the composting chapter.
In the previous example, you have already given the space.
Yeah, yeah.
So I assume that this is the ideal.
Actually, ideal is here.
The first problem.
Actually, here. So you have to keep 1 to 5 meter, and if you have 1 point, but if I have less than 1 meter, then it could be a like concern. Okay. Possibly, if it's an engineering design class, we would go back, okay, and try to see whether we can actually increase the height, okay, and give more space in between, okay. Yeah. Okay, so let's take 20 minutes break for your tea break, and then we'll continue with the next topic on anaerobic digestion. Thank you.